Hello again. Now I will run you through and give you a line by line explanation for the code file of my project. Let's straight away start with the libraries. So first I import the libraries which I will use the throughout. TensorFlow and Keras for modeling, Matplotlib and Seaborn for plotting, NumPy and Pandas for utilities, OpenCV for basic image handling, Plotly for interactive charts, and a few helpers like Pickle and JSON for saving histories and class mappings. I also import the specific Keras application models and layers I'll need, like VGG16 and functions such as preprocess underscore input where appropriate. You'll see that I have kept all my inputs together at the top, which helps keeps the notebook organized. So here I set the image parameters where the height and width is set to 224 and the batch size as 16. The 224 by 224 size is standard for models like VGG16, ResNet, DenseNet, and Inception. So it matches the input shape they were pre-trained on. Batch size 16 keeps GPU memory usage reasonable. I define training and test directory paths. My training folder contains one subfolder per class. The test folder is completely separate, so we never mix evaluation images into training or validation. This keeps our evaluation honest. So if you run this by yourself, remember to update these paths to match your own dataset location. Next, I built two data generators for training and validation. I use rescaling, a validation split of 20%, and standard augmentations, small rotations, zoom, width, and height shifts, shear, and horizontal flips with fill mode as nearest. So I create train generator with subset training and val generator with subset validation. For testing, I use a separate generator that only rescales and does not shuffle, so predictions align with file names. This way, the indices in test generator match the prediction order correctly. Well, I also then capture the class names from the train generator. So this mapping is essential because the models predict numeric class IDs and I need consistent way to convert them back to the readable letter labels. Well, just for a safety purpose, I also created a JSON file where I write the train generator class indices. So this prevents label order bugs when order loading a model later, ensuring the mapping from index to letter is always consistent. So in EDA1, I count how many images are there in each class and plot a bar graph. So this helps spot the imbalance, which could bias the model. In EDA2, I build a montage showing one sample image per class, a quick visual sanity just to make sure images are labeled correctly and loaded in the right format. As for the model architecture, I load the base with weights ImageNet. So this is for the VGA16. Include top as false and input shape as 224, 224, and 3. I freeze all base layers initially. On top of the base, I add a global average pooling 2D, a dense layer with a 512 ReLU units, a dropout of zero point 0.5 for regularization, and finally a soft max output with 1 unit per class. I compile with Adam at a learning rate of 1e minus 4, categorical crescent trophy loss, and track accuracy. So I use early stopping on validation loss with patience of 3 and restores best weights as true, and a model checkpoint that saves the best model based on validation accuracy. This prevents overfitting and ensures I always have the best performing weights saved. So I set the epochs as 15 and fit on training generator with validation data and callbacks. This is the first phase of training and only the top layers while the VGC16 base is frozen. Here you can see the results. I saved the training history with Pickle so I can load and plot it later without retraining. I also show how to reload the best model from disk. So this is important for reproducibility. Next fine tuning, I unfreeze the top convolution block, specifically block 5 and 4, and keep the earlier blocks frozen. I recompile with a lower learning rate than the previous one because weights I am updating are already well trained and I don't want to destroy that. So this allows the network to adapt high level features of ASL without damaging low level filters. Again, this is the result. Here again, I have saving the fine tune history as well. So now the second fine tuning, I load the best checkpoint from fine tuning 1, then unfreeze blocks 3 through 5, recompile with an even more smaller rate and add reduce on plateau on validation loss. So this staged unfreezing approach gives the network more freedom gradually, avoiding large accuracy drops. Again, I saving the history. So here I merge the histories from all three stages and plot and loss curves using the plotly. This is the code for that. So it shows exactly how validation accuracy improves or plateaus as fine tuning progresses, as you can see over here. Loading the final module for evaluation. And then I predict on the test set, build a confusion matrix and show it as a heat map. The diagonal should be, bright. That means correct predictions. As you can see here, off diagonal values show which letters the model confuses the most often. As for the evaluation matrix, I also print the test loss and accuracy over here, as you can see, and the classification report with precision recall F1 score for each letter. This is more detailed than accuracy alone. Finally, for VG16, I display some correctly predicted images. This makes the results more tangible. So from here, the pipeline, this is the general pipeline, and it repeats only the backbone, input size, and pre-processing and fine-tuning strategy changes over here. From here, I can show you for the RESTnet. This is for the RESTnet. Yeah, it uses its own pre-process input and keeps 224 input size. The head is identical, same training, fine tuning, evaluation. Rest of the processes are same. This is for the DenseNet. It has the same inputs, DenseNet's own pre-processing, identical head, same staged, fine tuning and evaluation. This is for the Inception. Same again, the input is same, but I unfreeze the from the mixed 7 layer onward. When fine tuning, I fine tune it with a learning rate of 1e minus 5. Everything else like training evaluation is consistent as the previous one. For the custom CNN, I use 160 by 160 inputs to reduce computation. It's built from scratch, so convolution blocks with batch normalization and dropout, then gap, dense 512 unit layer and softmax output. Same goes for mobile net with the input shape and its own pre-processing, the same kind of head and the same training pattern. As for real-time testing, finally, I load the best checkpoint here, which is 16, and set the image size to 24. I simulate real time by loading one sample image per class from a folder, predicting and displaying them with their labels in a live setup. These steps would run on webcam frames, resize, pre-process, predict, and map back to the letter label using the saved class indices. Now, if I just run this code, you can see this window has been popped up. Now, I just have to do the predictions just like this and see it is getting predicted on the screen. If you have to confirm, just press P. You can see the predictions are getting on the end as the text history. If you want to clear the character, you can press B, it's backspace. It's getting clear. If you press Q, it will quit. So this was my whole code file. As you can see, these are all the other sections involved. Since I have a time constraint, I did not actually explain every single thing, but so this was my whole of code file. These are all the sections which are there in the code file. As you can know, this is the VGJ16, which I've already guided you through. This is the RESTnet 60 section, configuration, dataset part, data general, everything, the architecture, confusion matrix, everything. This is the DenseNet section, model architecture. This is the Inception. It's model architecture. This is the custom CNN. It's model architecture. And at the end, this is the mobile net v2. This is the model architecture. So to recap, I used consistent pre-processing per model to match their pre-trained weights. I trained with careful augmentation, staged fine-tuning, and conservative learning rates. I evaluated not just with accuracy, but also prediction, recall, F1, and confusion matrices. I kept train validation and tests sets completely separate, and I saved label mappings to avoid mismatch when loading the models later. So here you can see are the images of the real-time testing results. So thank you for your attention, and this was it for my presentation.